Hello, my name is Jennifer Piani. I'm a PhD student at DePaul University, Chicago, and my poster is titled Autorevise, Video Annotation Refinement Using Signal Motion Patterns. The premise of the Autorevise method is that when motion signals are extracted from the subject of a video, the shape of the signals provide information directly relevant to localizing actions with high precision. This method has applications in class label refinement, activity boundary detection, and temporal video segmentation. The motivation for this work comes from a computational biology application using the C. elegans worm. This worm is found in every part of the world. It's approximately 1 millimeter in length. One of the most interesting things about it is that it has exactly 302 neurons with connections that are fully mapped. Biologists have the ability to deactivate individual neurons in the worm and observe their behavior changes. Our goal was to perform frame-level activity classification on videos of a worm specimen performing reversals, sharp turns, pauses, and forward motion. But we found that annotation errors were impacting the performance of our machine learning algorithms. We identified 3 types of errors: boundary localization, missing annotations, and mislabeled frames. Because even on videos of a simple organism performing simple actions, there was still ambiguity about the correct label. Our literature review indicated that annotation accuracy is primarily dealt with by using multiple annotators, but this doesn't provide high-precision localization. There are methods to evaluate potential errors that generate samples with labels and introduce known errors, but this may not be representative of the ambiguity in activity classes or real errors made by annotators. And there are methods to train a model to account for label jitter. But we really needed a way to measure label accuracy when there is no known ground truth to evaluate against. Our work extracts signals from a video. Signal processing methods have been used in activity recognition with wearable devices, but to the best of our knowledge, not with position data extracted from a video. Our method defines deterministic patterns, which consist of a set of defined properties. Each property in the pattern is compared to a signal in order to determine how well the signal matches the pattern. How well the signal fits the pattern indicates potential errors, and location where the signal was fit determines the starting and ending temporal locations for the annotation. This process is described in Figure 2. Autorevise begins at the first frame in a block of consecutive annotations with the same label. It searches the signal in both directions for the first property in order to determine the actual boundary at the beginning of the action. From the new boundary, it searches forward in a signal for the remaining properties, matching each property to a subsignal. The last property in the pattern is used to determine the correct ending location of the annotation block. If a property cannot be located in the signal or the subsignal doesn't correctly fit the property, it's an indication that these annotations are incorrect. In this case, the annotations are marked as needing review. Figure 3 describes how the starting and ending locations of a block of annotations are adjusted. The first property of the pattern was determined to be located after the annotation block had started, and the last property of the pattern was determined to be located before the annotation block had ended. The boundaries of the annotation were then revised. Figure 4 shows this method applied to a signal for the sharp turn action. There are 3 signals that represent the same Y location on the graph, but have been slightly shifted to highlight the revision that has been made. The green line represents the subsignal originally annotated as sharp turn, and the blue line represents the subsignal where the labels were auto-revised. This method works well in a human-in-the-loop process. A method of evaluation that involves comparing results directly against human annotations would not be practical here. Since the motivation for this work is that human annotations are inherently noisy, there is no valid ground truth to evaluate our model against. For that reason, we are introducing metrics for assessing annotation quality. The first, similarity improvement, compares the similarity of 2 sets of annotations from 2 different annotators before and after the Autorevise method is applied. Similarity is calculated on the original annotation sets by comparing annotations for each frame Then similarity is calculated on the Autorevise version of each set. Similarity improvement determines the change in similarity. The second evaluation method is boundary assessment. A tool was developed that shows a user clips of the boundary defined by both the original and auto-revised annotations. Then it asks them to choose the clip with the better boundary. Similarity is useful because when two sets of annotations are dissimilar, there must be an error in one of them. However, it is possible for two sets of annotations to be incorrect in the same way. So while it does indicate the presence of an error, it does not necessarily demonstrate the absence of an error. The boundary assessment method is a direct measure of accuracy, but it has the drawback of requiring additional human effort. In our human-in-the-loop evaluation of similarity improvement, 3 annotators for 3 videos were asked to use the Autorevise method on their annotations in 3 passes. A single pass included Autorevise, then reviewing the annotations, paying attention to those labeled needs review. We evaluated Autorevise with and without a human-in-the-loop method. Both methods did show improvement. However, combining Autorevise with human-in-the-loop showed the greatest improvement. These results are in Table 1. The boundary assessment was conducted with 50 clips across all videos and annotators. Samples from the start and end of the clips were identified. 6 to 10 clips of each activity were selected. 3 users were asked to use the utility, then indicate whether the human annotated or auto-revised annotations had defined a more precise boundary. They had the option to select not sure, since it was useful to find out if it was too difficult to discern a boundary. 2 assessments were conducted, one on samples from annotation sets by a single annotator and another on samples from a set created from the majority vote of 3 annotators. The results are in Table 2 with and without including the not sure option. We can see that in both experiments, Autorevise improves the boundaries of annotated activities. Beginning the Autorevise process with less noisy annotations by using the majority vote annotation set improves the boundaries more often and with less uncertainty. This work demonstrates that patterns in motion signals representative of activities are present and can be used to improve annotation boundaries and identify potential errors. This work introduces new metrics for assessing annotation quality: similarity, similarity improvement, and boundary assessment. Future work will approach this problem with machine learning, incorporating these new metrics into a loss function. We are currently expanding this work from C. elegans videos to videos of human activities and more complex data sets. Thank you for listening to my presentation on Autorevise.